Okay, we're continuing with Chapter 3 in the algebra textbook. The first portion of Chapter 3, the first 4 sections, was all about polynomial functions. So now that we've finished learning about polynomial functions, we're going to talk about the second portion of the title of this chapter, rational functions. Okay, so obviously a rational function is going to be some sort of function where the expression in the function is made up of one or more rational expressions, some sort of rational expression. So let's start by reminding ourselves of what exactly a rational expression is. So in pre-algebra, we went through the different categories of expressions. So there was polynomial expressions, linear, quadratic, radical. Okay, and so the different term types in these expressions were you had x to a whole number power, so like a positive integer power or 0. Those were associated with polynomial expressions. You had x to some rational exponent, which was associated with radical terms and expressions. Okay, in x to a negative integer exponent, these types of terms were associated with rational expressions. And the idea was that in general, a general rule for classifying or naming expressions was that one rational term would take precedence over polynomial terms as far as naming. So you could have all these polynomial terms, but if one of the terms is rational, then you're going to call that a rational expression. Then from there, a radical term would take precedence over a rational term. So if you had an expression with polynomial terms and rational terms, but there was just one radical in that expression, then you would call that a radical expression. And then from there, if you had one exponential term, that's going to take precedence as far as naming. And then from there, the logarithm would take precedence. The exponential would take precedence over the radical, the rational, and the polynomial. The logarithm takes precedence as far as naming over all of these. Okay, now the official mathematical definition of a rational expression was that it's an expression to where if we think about a single term rational expression, so one term, then it's rational if that term is a ratio of polynomials. But the problem with this definition is that it's not very intuitive, in particular for non-math majors, because according to that definition, the number 3 is a rational expression. All polynomial expressions are rational expressions because this is a ratio of a 0th order monomial with leading coefficient 3 to another 0th order monomial with leading coefficient 1, right? And so that's why informally we looked at a rational expression as being an expression that is made up of terms like x to a negative integer exponent. But even this definition here, this informal definition, is not foolproof in the sense that, so if you had 1 over x plus 3, or x squared, 1 over x squared plus 3, well, you can't really write this as an x to the minus 2. The best you can do is like that. And so an extension of this informal definition of a rational expression as being made up of terms of x to a negative integer power is that it's a rational expression is going to have a term in it where there's at least one variable in a denominator, with that variable being raised to a positive integer power. That's it. That's the informal definition of a rational expression. Okay, so with that, then what is a rational function? So, okay, a rational function is, so f of x, we could isolate the y on one side. This, you could say that this is y is equal to, y is by itself over here, so we can write it as a function, f of x, and we look at just the basic bare bones rational function as this single term rational expression. So obviously you can extend functions however you want past these basic definitions. You know, you can have a rational function can be a sum of or difference of multiple term rational expressions, but fundamentally the rational function is f of x is equal to this single term rational expression or ratio of polynomials. Okay, but again, because this definition here mathematically, technically includes the constant function as a rational function, because this is a ratio of polynomials, then informally, we're going to look at a rational function as being f of x is equal to this single term here that it's a fraction, and in the denominator of the fraction, there's at least one x raised to a positive integer power. If that's the case, then we call that a rational function. So with that, you can see that here's some examples. F of x is equal to 1 over x is a rational function. This is another rational function. You have an x squared and an x to the first in the denominator of this fraction. Here's another rational function. Okay, now, however, just note that if you had something like, okay, well, yes, this has a variable in the denominator raised to a positive integer power, but with the radical here, the radical is going to take precedence as far as naming goes. So this expression here, we wouldn't call rational. We would call this a radical expression. And so obviously with that, then we wouldn't call this a rational function. I mean, yes, as we've talked about, in general, you could look at this expression as it's got a mixture of rational and radical character. It's got a polynomial in the denominator. It's got a radical in the numerator. So it's a fraction with a mixture of the character of rational and radical. You could look at it that way, but just as far as the way we officially apply names to expressions and equations, etc., and functions, this we would call not rational, but radical. Okay, now next, what we want to do is analyze the different attributes of rational functions, as well as analyze the graphs of the different forms of rational functions. So a good place to start is thinking about the domain of a rational function. So with polynomials, the domain was all real numbers. And put any real number you want, no problem. And that actually extends to even complex numbers as well. You can input any number in the complex plane into a polynomial, and you're going to get an output. Okay, and so with that, then, since with a rational function where we're only going to have polynomial terms in the numerator and denominator of a fraction, then what you can see is that the only domain issue comes into play in that q of x can't equal 0. The only issue here is dividing by 0. You can't divide by 0. So with a rational function, you can input any x you want, as long as that x doesn't make q of x equal 0. All of the x values that make the q of x equal 0, you can't input, but anything else is within the domain. Okay, so that's a good place to start for analyzing rational functions. Now, the next thing we're going to want to think about is, so when we were analyzing polynomial functions, we thought about what happens as x approaches infinity. What does the function do? And what happens as x approaches negative infinity? What does the function do? And we're going to actually want to do this same analysis for rational functions as well. We're going to want to do this, analyze what any function does as x approaches positive or negative infinity. But with the case of rational functions, we're also going to want to analyze what the function does as x approaches any of the values that make any of the x values that make the denominator equal 0. Okay, so you could, let's say we have this graph here. Okay, let's say we found that the denominator of a rational function equals 0 when x is equal to a and when x is equal to b. Because there could be multiple x values. It just depends on what the expression is in the denominator. Okay, so what we're going to want to do then, one of the things we're going to want to analyze is What does the function do as the input x approaches these values? But there's two scenarios. For each of these. You could be approaching from the left, or you could be approaching from the right, and same here. So we're going to want to analyze both. We want to analyze both directions for each of these values. And the notation we use for this is that we're going to say, so we're analyzing as x approaches the value a, and if we're coming from the left, that means we're coming from the negative direction, so we're going to put that. And if we're coming from the right, that means we're coming from the positive direction. We're going to put that. It would be the same idea here. Okay, so now we can start to think about what we expect to see a function do as it approaches a value like this. Let's say that q of x is equal to 0 when x is equal to a, so x can't be equal to a, and x can't be equal to b. That's when q of x is equal to 0. Okay, in some cases, one of the scenarios that we would expect to see as far as x approaching a value like this is that we would expect to see that, okay, so when x approaches a, that q of a is equal to 0. And then, but if p of a is not 0, just any number other than 0, then we're going to expect to see the magnitude of this ratio balloon towards infinity. Because we can never get to a, right? We can never be at a. The function doesn't exist, right? It's outside of the domain. But if we're extremely close to a, then the denominator is very, 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 very small, and the numerator it's not 0. It's just some normal number, some non-zero number. Then a non-zero number divided by something extremely small is a huge number, that's what we call infinity. And so in these cases, the result is that at like x is equal to a, if this is the case, where again you've got a non-zero, you're approaching a non-zero number up here, but 0 down here, then you have what's called a vertical asymptote, which means that you're going to be getting closer and closer and closer to a, very close to a. And as you're doing this, the function is just ballooning to positive or negative infinity. And it's asymptotic. It's getting closer and closer and closer and closer. But it's never getting to a. It never equals a. It can't, because you can't divide by 0. It has this asymptotic behavior. In this case, it's a vertical asymptote. Now, it could be the case, though, that as you get close to a, you're not ballooning to positive infinity. Maybe you're ballooning to negative infinity. And that's something you'll analyze. It's going to depend on, so q of x never equals 0, but it gets really close. Well, is it approaching 0 from above or below? And then is p of x isn't approaching 0 as x approaches a or b, but is p of x negative or positive? So you have to just analyze it and see. It could be the case that on both sides you're approaching positive infinity, or both sides you're approaching negative infinity, or they could be the opposite, like this. Okay. Now, what you can think about though is that it's not always going to be the case that for the x, if the function is approaching an x value that makes the denominator 0, that you're going to have this vertical asymptote behavior. Because it could be the case that as that the denominator approaches 0, but the numerator does also. And that's going to have a different kind of behavior. Because in that sense, yes, the denominator is getting really small, but so is the numerator. So you don't have some non-zero number divided by a tiny number, that which is like infinity. It's going to depend. It depends on, well, which one is approaching 0 faster. It just depends. That's a separate analysis. Okay, but now it also could be the case that maybe you have a rational function to where the denominator, there are no x values that make the denominator 0. Like this, for example, x squared plus 4. There's no real number x you can input into x squared plus 4 and get 0. Okay, so these are the different forms of rational functions that we're going to want to analyze. They're all going to result in slightly different graphs. Okay, but now this asymptote behavior that we can see with certain rational functions, also with rational functions, because we're dealing with a ratio, we can also see in certain cases horizontal asymptote behavior. Okay, with a horizontal asymptote, this comes into play when you're analyzing what the function does as x approaches infinity or x approaches negative infinity. With polynomials, the only result could be that as x approaches infinity or negative infinity, the function is going to balloon to positive or negative infinity as well. That's the only possible result when it comes to a polynomial. However, because a rational function is a ratio, there's certain cases where we see this infinite behavior act differently than strictly just ballooning to positive or negative infinity. Okay, so sometimes the result is a horizontal asymptote, what's called a horizontal asymptote, which means that, as we're going to see with certain rational functions, as x approaches infinity, the function is going to asymptotically approach a horizontal line. It's going to get extremely, extremely close without ever touching that line. Extremely close, coming from above or below. Again, this is as x approaches infinity or negative infinity. So with a horizontal asymptote, as x approaches positive or negative infinity, the function is approaching some number, some constant number. With vertical asymptotes, it's the opposite. As x is approaching a constant from the left or from the right, the function is approaching positive or negative infinity. But in both cases, it's this asymptotic behavior. Okay, and so with that, you can see that there's a few different scenarios that we need to analyze with rational functions and take a look at the corresponding graphs. However, we can start by taking a look at a typical graph. Here's a typical graph of a rational function. This is f of x is equal to 1 over x. And so, okay, the domain we can see is going to be all real numbers except x can't be equal to 0. At x is equal to 0, you're dividing by 0. And since 1 is always just 1, then we can see that the vertical line x is equal to 0 is going to be a vertical asymptote, because as x approaches 0, gets really close to 0 from the left or the right, you're going to have 1 divided by an extremely small number. That's infinity. And what we can see is that coming from the right, x is going to be an extremely small positive number, and since 1 is always positive, the function is going to be approaching the vertical asymptote going to infinity coming from the right. But then coming from the left, x is going to be very close to 0, but in the negative, from the negative side. Positive 1 divided by a tiny negative number is going to be negative infinity. So we can see how the function acts as it approaches the x is equal to 0. It's a vertical asymptote. Okay, now next we can analyze what the function does as x approaches positive or negative infinity. And what we see is that we're going to have 1 divided by some positive or negative infinity, which in either case is going to be some number, some extremely small number. So we're going to have a horizontal asymptote in for this function as well at y is equal to 0. The horizontal line y is equal to 0. Now as x approaches positive infinity, you'll have a positive 1 divided by a very large positive number. That's a very small positive number. So we expect the function to approach y is equal to 0, the horizontal line y is equal to 0 coming from above, and that's what we see. Now, when x is approaching negative infinity, you have positive 1 divided by a negative number. So in this case, we expect x to approach, as x approaches negative infinity, we expect the function to approach 0 coming from below, and that's what we see. Okay, and outside of that, there's really nothing else to analyze. There's no x-intercepts, there's no y-intercepts. All we could really do was maybe plug in a couple of values, like plug in x is equal to 1 and x is equal to minus 1. Test for symmetry. This does look like it's an odd function. So get some extra points to help aid in sketching the graph. But other than putting in the asymptotes and drawing the function's asymptote behavior, that's really it. That's the only main features of this graph. Okay, now what about f of x is equal to 1 over x squared? Well, okay, in this case, you can't divide by 0. That's the only x value you can't input. And since we have a positive 1 up here, we see that x is equal to 0. That's going to be a vertical asymptote. The vertical line x is equal to 0. Okay, now as x approaches 0 from the left or the right, since 1 is positive, the function is going to balloon to positive infinity because x squared is always positive. And as x approaches infinity or negative infinity, still the denominator is always going to be positive. But when you have 1 divided by a huge positive number, that's going to approach 0. So we're going to have a horizontal asymptote at y is equal to 0. And there we go. So there's 1 over x squared. As x approaches negative infinity, the function approaches 0 from above. As x approaches 0 from the left and the right, the function approaches positive infinity. As x approaches infinity, the function approaches 0 from above as well.